Okay, so I keep forgetting this. So these are the X-ray optics as are available. We'll talk about a couple of them, which are the more important ones. So glancing incidence reflection, we've talked about. When your refractive index is a little bit less than, when it's less than unity, or even a little less than unity, you get total external reflection. And depending on delta, there's a critical angle here, which for X-rays with the values of delta that we have, could be like in the EUV, it could be like 3 or 4 degrees. For hard X-rays, less than 1 degree. And I'll briefly show the slides again. There are multi-layer interference coatings with a differing refractive index, so what we call high Z and low Z, because the Z of the ions, or the atoms rather, of the atoms dominates what is the refractive index, okay? So with alternating layers, you can get a very weak reflection from each interface, from each side, on the high Z, low Z, low Z, high Z, wherever there's a change in refractive index, there'll be a slight reflection. But if these layers are nice and flat, then whatever the incidence angle is, all of these reflections will add up in phase at the Bragg angle, which is a combination of the wavelength, the d-spacing, and the angle of incidence. And in general, for hard X-rays, you can't get normal incidence. Even soft X-rays, actually soft X-rays now, I'll show you, you can get reflections of 20% in some cases. Years ago, you couldn't do that at normal incidence. But at hard X-rays, basically, the main thing you can do is if you put one of these coatings on some surface, you will not only be able to get a reflection, a critical angle reflection off the surface, which would be a small angle, but you at a larger angle, you'll get the multi-layer thing. So we'll see a reflectivity curve later where you can, make use of multi-layers even at hard X-rays, but not at normal incidence, at some small angle, but not as small as the critical angle, okay? Then there are capillaries where you have multiple reflections inside the capillary, glass capillary, and usually they'll come in bundles. So we don't typically use them so much in the synchrotron and FEL worlds or the high harmonic worlds. But for people who are interested in doing things not on the micron scale, but tens of microns or 100 microns, they're quite useful for redirecting radiation. And all of these are glancing incidence reflections. So even though there's a multiplicity of them, they still work quite well, and you can bend X-rays around a sharp angle. So those are all reflection. Diffraction, we're going to start with the grating because it's the easiest thing to understand, okay? And we'll basically find that for radiation coming in at some wavelength onto some grating of some period, which when I show black like this, it means this is absorbing and open, absorbing and open. There'll be diffraction at the grating angle, okay? And that angle is lambda over d. And notice that the smaller d is, the smaller the period, the bigger the angle. So small openings, small periods will result in large angles. That is interesting to note, not because we use transmission grating so much in transmission, we just don't use them that much, but this idea that this is the angle, the diffraction angle goes inversely with diameter helps us to understand the zone plate. Because in the zone plate, we're showing here illumination, and the zones are kind of big in the middle and smaller, and the outermost zones are the smallest. And so the incoming radiation diffracts from them through the largest angle. So here's a large angle. This is the largest of the 3 arrows shown. This one's coming straight through the middle. There is straight through radiation coming through, as we'll see, and there's also diffraction in radially outward. But the diffraction angle for this outer arrow here is the biggest deflection angle. And it's because the outer zones are the smallest. So according to this formula, they should get the biggest deflection. Okay. And this says that this angle is lambda over 2 delta r. So this is not d. This was lambda over d. This is D here, the outermost zone, the littlest, the tiniest, or the thinnest zone, we call delta R, capital delta R. And so you need for a period, you need one open and one close. And so it's 2 delta R approximately. So that's the deflection angle. And if you've worked with microscopes, you know that resolution depends on lambda and numerical aperture. And this is numerical aperture for us. There's no refractive index in this medium, or it's almost 1. So, so we're going to get the numeric, this will be the numerical aperture. Okay? And it'll be lambda over 2 delta R. Okay, then there are crystals. So crystals are extremely valuable, especially for hard mostly, and for hard X-rays. And you can get, again, at the Bragg angle now, you can get a 90 or even 95% reflection off one of these crystals of sufficiently narrow radiation, okay, and collimated, sufficiently well collimated. And this combination of 2 crystals is called a double crystal monochromator. So you can use this as a means to narrow the radiation from an undulator from 1 over n bandwidth to something like 1 over 10 to the 4th, or even narrower. So we'll briefly mention this also. What we haven't mentioned so far is refraction. But actually, for hard enough X-rays, the best performance would be like at 20 kilovolt, but people use them even below 10 kilovolt, where if you have a lens which for visible light would be a negative lens producing divergent radiation, for X-rays, it produces converging radiation. And there's a focal length that's equal to the radius of curvature over 2 delta. Okay, the delta is the refractive part. So one of these is kind of weak. Delta is small, as we know, 10 to the minus 3, 10 to the minus 4. So really long focal length. But a husband-wife team at ESRF in France, a Russian husband-wife team, the Snigarevs, Anatoly and Irina, came up with this idea of stacking a whole bunch of these together. And so these ellipses, actually, the narrow part is here, and up here it's a little bit. So this narrow in the center and broader outside, that's in this region, okay? And so they stack up 20 or 30 of these things. They make them out of very low Z materials, like beryllium, for instance, so that they don't absorb. And this is where the action is. This is where the focusing is. And now the focal length is the same R over delta, 2 delta, but it has an N, where N is the number of these focusing elements. Okay? So we often call them a Snigarev lens, but they call them, and many others call them, compound refractive lenses. Any comments? Okay, so we don't have to go through this, but our glancing incidence diagram was as shown here, where the refractive index was at the top, okay? And the light coming in was bent away from the normal. Rather than with visible light, refractive index 1.5, it would have bent towards the normal. Now we bend away from the normal. And so if you come in at a small enough angle, this arrow, the reflected wave will also match angles here, right? Angle of incidence equals angle of reflection. But the refracted angle obeys Snell's law. And if we make this angle theta small enough, this will run along the surface. And now there'll be an incident wave, a reflected wave, and the refracted wave will just run along the interface with only an electric field which exponentially decreases into the material. So it doesn't go in very far. There's not much absorption. A wave that runs along an interface with a normal fields outside the interface, but exponentially decreasing inside, is called an evanescent wave. And you can make waveguides out of these things, okay? And so there's some critical angle for which it just runs along the interface, and that's much reduced absorption. But if you make the angle even smaller than that, rather than be at the critical angle, maybe at half the critical, the evanescent decay is even sharper and the reflection's even better, okay? So we went through that little bit of algebra and we got this critical angle of square root of 2 delta. We gave the example of gold at a kilovolt, where we look up delta at the website that we always go to. And for 1 kilovolt in gold, it was 3.7 degrees. And so if you go to harder X-rays, this number will drop very rapidly. Remember, it goes as more than lambda squared. So if you went to 10 kilovolts, this is going to get a lot smaller. The angle is going to get smaller. On the other hand, if you go to an EUV wavelength, delta depends, but delta could be bigger and the angle could be bigger. And these were just some practical curves which showed for different materials what happens if you include their absorption edges. So these are numerical things. Okay, and this was an example of how astronomers use nested optics to image literally far off objects. In this case, this M81, I think it's called, the spiral galaxy. Okay, but what's shown here is the optics, each of these surfaces can be coated with a different material, and depending on the angle of incidence, can provide very sharp cutoffs, which are good when you're trying to figure out what is the spectrum of what's coming out of here and how that might relate to the elements that are there or between the galaxy and the telescope. But anyway, these very sharp cutoffs will sort of block anything from higher photon energy. So in this region, you could have X-rays of, let's say, 1, 2, up to 2 kilovolts, but everything above 2 kilovolts will not get through that channel to the detector. But this one could go up to 10 kilovolts. So you could see where you could have images that represent different photon energies, probably combine them with some filter combinations so you could do it even finer. And you get a lot of information about temperature in whatever part of the object you're interested in looking at. Okay. Whoops. So you can use two curved surfaces which are orthogonal to each other, and together, one curved in one direction, one curved in the other. You can form a real image. They're often used in high magnification, not as shown here, but it's hard to show a 50 times magnification. But they're very often used in microscopes or telescopes or something like that with very, very long focal lengths. And the best shape to use for point-to-point focusing is an ellipsoid. The difficulty is it's easy for people to polish surfaces because the surfaces need to be absolutely smooth here. There can't be any little wobbles or noise, roughness rather. You don't want roughness and you don't want polishing marks. You want a really good surface of an ellipse or whatever the surface is you want. And until recently, it was not possible to get a really good surface. It's only in the last, say, 10 years that the team at the University of Osaka has perfected the making of complicated surfaces, which are both have the figure, that's the word that you use for the shape, have the figure, but polish out the roughness and minimize the markings from the polishing process, because they use a chemical processing now, not a rub, or rub even with a tool. So that group at Osaka under Yamauchi-san started a company called JTEC, and basically all the synchrotrons and all of the FELs around the world, if they want to have the best focus or the best collimation, they go to JTEC and buy an optic. And mirrors are, of course, are used in beamlines. That was the only purpose of this slide. We use a lot of mirrors in our beamlines, both as synchrotrons and FELs, and to some degree at the high harmonic sources. And this is just another one, showing all the places where we use a retractable mirror so we can share between different end stations, reflective gratings, another bendable mirrors, okay, for re-imaging the source onto the sample, etc. And this is for the hard X-rays, of course. They do use a mirror because they also have to share beam time, so they have a mirror that they can insert, but then they have a double crystal monochromator. So they have, actually hard X-rays have minimal optics. They have the double crystal monochromator, and they'll probably have some deflecting mirror, but they may not have any more. That may be the only optics they have. They could possibly have more. Okay. And then this is from the Osaka group, and this is done at spring 8. So it's an undulator at spring 8, and they have shown that they can, with these crossed mirrors, which they've tried many kinds, ellipsoids and you name it, and some with multi-layer coatings, which allowed them to get larger angles and therefore higher numerical aperture and smaller spot sizes. They've tried so many, they've successfully demonstrated so many things. And this is work where they showed that they could get their focal spot down to 7 nanometers, actually in both planes. And we're not going to read this, but it just says more of the same. That they got, in one direction, they got a width of 7 nanometers at 20 kilovolts. Actually, later on, they got it in both directions. So now some comments about multi-layers. I'm going fast because I want to get to the diffractive optics. So multi-layers, when they were relatively new, which would be in the early 1980s, is that right? Yes, around 1980 and 1981, I think. The first mirrors came on. This is one of the first made in Berkeley. Not one of the first, but not the very first, but it was made by Tai Nguyen, who was a student initially in MSc, and then he switched to AST. And this is a tungsten carbide multilayer. But where the multilayers fit in the larger view at that time was that there was a void here between, let's say, 25, 30 EV and a few kilovolt. There was no good reflecting surfaces at that time for large angles, for normal incidence. So this was normal incidence reflectivity. These are the kind of coatings that you had, mag fluoride and the like, for the ultraviolet. And then for hard X-rays, you have natural crystals, but there wasn't anything for normal incidence in the middle until the multilayers came along. And they best filled in around the 13.5 nanometers that we've talked about, and 11.5 we talked about. But later, Eric Gullickson at LBL came up with coating processes for the soft X-ray region that got up to, in this case, to about 30%, as I recall. And that's in the book. Okay, so here's a multi-layer coating. This is showing very sharp interfaces, and it's showing the Bragg condition. Okay, so again, this is electron density. So there's two materials here. This one would be the low Z silicon, the high Z molybdenum in this case, showing very sharp interfaces. If you had very sharp interfaces, which you don't, by the way, when you're laying these things down, putting the ions, laying one coating on top of the other, there's interpenetration between the layers. And so these are never so sharp. They're kind of rounded off to some degree, depending on what you do. But if they were sharp, or as a measure of the sharpness, if you did a Fourier analysis of this, very sharp would show you'd have all kinds of higher orders. So you could reflect not only at this angle, but some much smaller angles would reflect off Fourier components, which would be 3 times or 5 times this. So in fact, they use that as a measure of how sharp the interfaces are. They scan as a function of angle and see what kind of reflections they can get off the higher orders of this profile. This is one that we've shown many times. This is the polysilicon one that got to 70% reflectivity. And it's the enabling technology for the EUV lithography. But these same coatings are used, so it was used in the EUV lithography, but those same kinds of coatings are used for solar physics. So this is the so-called trace telescope that's orbiting Earth at all time and takes images every few seconds, and they're tuned. The wavelength of the optic, a 2-bounce optic, is at this case at 17 nanometers, which is matched to the emission lines of 8 times ionized iron, which is a common, iron is the highest Z equals 26. Iron is the highest element of which which there's copious quantities in the cosmos. You go beyond iron and it falls off very rapidly, and they need other processes to produce them. Okay, but anyway, so iron, there's a lot of iron in the sun's atmosphere, and that's what was used here. And we saw beautiful features and more of the same here. So here's a view of the telescope. Light coming from the sun, X-rays coming from the sun, or EUV, bouncing off, two-bounce system onto a CCD, and here's a gigantic loop. These are some of those soft X-ray. This is a reflectivity curve for chrome scandium from Eric Gullickson that I was mentioning to you before. So this edge is at 398 eV, and just to the side of it is this peak that got up to 30%, 32%. So this was a major achievement. This is for near normal incidence, and these are just some of the parameters, 81 degrees. Okay. This is at 1.49, 1.5 kilovolt. This is just a calculation, but these, I don't know, I lost the measured curves, but they look very similar. But this is the reflectivity as a function of angle. So this is the critical angle performance we were looking at with the first few slides. And then normally there'd be no reflection beyond that. But on this surface, the surface that's producing this was placed a tungsten carbon multi-layer coating. And these are some of the parameters of it. And it's optimized for 1.5 keV, and it gives a nice peak. So it's not 100%, but it's pretty good. And it's at a large angle, which means a larger numerical aperture. So if you were trying to resolve something about the sun or some stars someplace, this would give you a higher angular resolution by using not the glancing incidence reflection, but the reflection, the Bragg reflection off the multi-layer. And this is, for instance, an example. This was at the ALS. It was the first beamline at the ALS, and it used a Kirkpatrick-Baez pair of two curved mirrors, and it used coatings. There were 3 sets of mirrors, all coated. So one set was coated for 8, one set for 10, and one set for 12 kilovolts. So taking bending magnet radiation, which we recall the ALS, if you're going out to 4 E crit, 4 times the critical energy, you were only down a factor of 10. That would be about 12 kilovolts. You were still getting really good emission from the bending magnet. So in the early days, there were no undulators working at the ALS yet. Something over $100 million had been spent to build this facility, and people were wondering when they would get science. And so Jim Underwood and Al Thompson put this together, where they used the KB pair that Jim provided, and it was his idea, with an aperture here to set what would eventually be the resolution here. They wanted to get a micron resolution here. This was a big magnification, so this would have been a much larger pinhole aperture. And then these optics focus the radiation onto the sample, which is then raster scanned, and what's observed is fluorescent emission, which is going into all directions. But for instance, depending on the photon energy chosen here, for instance, with 8 kilovolts, you would ionize, you would knock out a core electron in all of the atoms there, no matter what they were. And they would all fluoresce, all with different characteristic photon energies. And then you have as big a solid angle as you can get, detector to catch the fluorescent emission as this thing is scanned. And this is the example I think I showed you before of fluorescent emission of an iron solar cell contaminated with little bits of iron. Okay, and one of the nice things about this is it's super sensitive. There's no background noise. There's no electrons involved here. It's photons in and photons out. So the noise level is quite low, and the system is sensitive enough to do femtograms per, it says meter squared. That's not right. It has to be micron squared. Boy, I can't get rid of all these mistakes. Yeah. So, right. So that was a big success. And again, it was the first beamline at the ALS. It was also the first time, I think, that anyone in the synchrotron world had made a microprobe using these double mirrors. Now it became very popular. And of course, and we saw now that the resolution has gone from a micron in these early experiments to less than 10 nanometers. This is how you make the multi-layer coatings. This mirror substrates are put on a top, a meter, maybe a fraction of a meter in diameter, maybe. Actually, for some mirrors, could be actually more than that. And there are substrates in different places, and they rotate, as the table rotates, the mirrors rotate. And then they take turns going over the high Z material and the low Z material, where there's a discharge going on. I think there's an argon gas here, and there's an ionization that drives the discharge in both cases, and the argon is ionized, and the ions, the argon ions, IONS, come in and pound into, are accelerated by electric field and hit the target, the raw target material. So for instance, tungsten and carbon, or moly and silicon, some pair. And so they're spewing out atoms, ions of this material, but they're very low energy. They're sputtered out, and they go up. There can be masks. There are always masks, actually, to sort of shape the radiation, the particles coming up. And then they hit, strike, and are adhered to these mirrors as they go by. They rotate for uniformity, okay? And then as this mirror goes over this one, it gets, let's say, the high Z coating. And then as it rotates around in this position, it would get the low Z material and then go around. So if you wanted 40 layer pairs, you'd go 40 times around. If you needed an intermediate material like B4C, you'd need another head in the middle here to get that, okay? Maybe on both ends of it. So that's how you make them. You also have to measure them. So this is beamline 6.3.2, I recall. And this is Eric Gullickson, by the way. He's the one who maintains that web page we use so often. And this is Andy Aquila, who is now at SLAC, at LCLS, and Franklin Dollar. Franklin is a professor at Irvine, okay? And this is Yanwei Liu, who is also at SLAC, and he contributed to lots of the things we've talked about here, the coherence measurements and multi-layers for attoseconds, et cetera. In fact, Andy's PhD thesis, a big contribution to it in the end was the first measurement. He made the multi-layer coatings, the axially, the two mirrors, one inside the other, that could be used with a street camera for the high harmonic, and measured the 80 attosecond. It was the first time anybody, where any team, it was led by the group in Garking, of measuring a sub-femtosecond pulse accurately. So they got down to 80 attoseconds. Okay, so for monochromators in the soft X-ray and EUV region, we generally use glancing incidence gratings, so reflection gratings, okay, coming in at glancing incidence and then reflecting off the gratings. And these are not simple straight lines as they would have been years ago, but they're shaped to put more of the radiation in the order that you'd like. So the M equals 0 is just a straight reflection, and then M equals 1 or 2 or -1 or -2 are the different orders, okay? And so, and this is the grading equation, okay? And for instance, on many of the beamlines at the ALS or any of the other low energy beamlines around the world, they're probably using a grading, grading monochromator. And here's a bunch of references, okay? The early ones are in books. In case I haven't told you about it, this book by Hecht on optics, it's got I don't know what version it's in now. It's a very, very popular book because it has such great diagrams and great explanation, and it doesn't overdo the mathematics any more than it has to. And then these are just, Bourne and Wolf is one of the Bibles, and George Stroke there's a relatively long article, but still. And Mike Hetrick played the major role in determining what they're called, inventing and designing what are called varied line space gratings, okay, which have these interesting properties. And these are some papers from China, by the way, from Tongji University in Shanghai. Okay, so now what we're going to talk about, and we have some time, is diffractive optics. So our main interest, of course, is pinholes are always an important for us, and we've spent a lot of time on that, so we'll just spend a little time here. The zone plates we haven't, so we're going to spend time on that now. The grating we're only going to put in there because we want that formula for the diffraction angle as a function of d-spacing, which is going to help us to understand the zone plate. So here is our transmission grating, shown here as being opaque or having absorptive zones, equal lines and spaces, so there are lines going into the board, into the screen. Collimated radiation shown coming in here. And then there's some absorption. Half of the light is absorbed just by area, right? So 50% is absorbed. That's what it says down here. Of the light that gets through, some of it goes straight through, and some goes to a plus order, and some goes to a minus order. But there's also a third order, a fifth order in both directions. There's no even order because the openings and the closing absorptive parts are equally wide. But if that were not the case, you would have +2 and -2, +4, -4, etc. Okay. If you look for where is there constructive interference at some angle like this one, you'd say that, okay, the radiation coming through each of these openings has to add up constructively at some angle. What is that angle where the additional path length from this one going up to this one, what is the extra path length? Where is it exactly a wavelength? That would lead to constructive interference. So you make this diagram. So actually the diagram is made for going down. For instance, between this ray and this ray, you could make this little triangle there, where D is the distance from the middle to the middle of the open zone. The extra path length this way has to be a wavelength for constructive interference. And this is the period, okay? And so what is that angle? So it's a right triangle. You solve for the sine, and this is what you get, okay? So these various orders are going to satisfy this grading equation. So it's different than the Bragg equation, okay? If you do a diffraction efficiency calculation using Kirchhoff integrals, which are in the book, but we didn't touch on them. But anyway, if you do those things, you'll find that the efficiency to the various orders here is as follows. First of all, 50% is absorbed. There's nothing going to the even orders because of the reason we said. And the amount going to the odd orders, for instance, for m equals 1 or -1, either case, the efficiency is 1/π², so roughly 10%. So we often say that the zone plates are roughly 10% efficient if they're using opaque structures like that, and we're operating in the first order. Notice that, for instance, in third order, you'd be down a factor of 10. So you go from 10% efficiency to 1% efficiency. But we'll see an example of where that gets used for third order, which would be a higher angle with a zone plate. And the reason is the angle is larger, so the numerical aperture is larger. So the resolving capability is larger. Essentially, the numerical aperture is larger. Any question on this before I jump? Okay, well, here is the more interesting thing then. Here is a zone plate with collimated radiation coming in, which, by the way, we would recognize collimated radiation is spatially coherent, right? It means that there must be a small source very far away behind here, and so far away that the fact that it's not quite collimated doesn't matter, that this diameter is small compared to that. And by the way, for instance, at a beamline, at a synchrotron, typical diameter for one of these zone plates is 100 microns or less, and the distance back to the undulator might be 20 or 30 meters, so the angles are pretty small. Okay, so what we'd like to know is, what if we're writing this pattern, and I'll show you these are made by writing with an electron beam into a resist to get a pattern, and then doing some developmental chemistry, doing some chemistry to develop the pattern, and then maybe coating on some metal like gold or nickel or something like that. But anyway, what should the radii be labeled from? And by the way, this is R1 is the edge of the first dark absorptive region. R2 is the leading edge of the next one. Then this would be R3, etc. The outermost, and they're all, R sub n would be the general zone. The opening in the outermost area we call delta R. So this is meant to match with the white region here, denoting a transmissive region. And the total diameter is 2 times R with a capital N, subscript capital N, meaning it's the nth zone. Okay, the outermost, capital N means it's the last one. So if we had 100 zones, this would be 100. So we're going to use this delta R a lot, because this outer zone, it's a half period, and it's the smallest period, so it's setting the biggest angle of deflection, which, as we commented on, is numerical aperture. So how can we figure out what is the formula that we need to make these different radii? Well, when we look at these rays here, we see that these are right triangles. Okay, there's some imaginary focal spot, which we've labeled a distance f away, but we don't know where that is yet. We'd like to find out how that depends on our zone widths and our wavelength. But each of these is a right triangle, so we can apply the Pythagorean formula. Oh, and each of the zones is the focal length plus a half wavelength on the last one. So going from here to here, you've added a half wavelength, and then another half wavelength for this one, and another half wavelength for this one. So they're alternating between opaque and open, opaque and open. But so each of these rays that are shown here are the focal length plus whatever n was, half wavelengths for each half zone, for each half period. Okay. So now we use Pythagorean formula. We square this, and that's got to equal to R sub n squared plus f squared. So this is our Pythagorean formula here. A squared plus b squared equals c squared. Okay, whoops. You see my mistake. In the Pythagorean formula there, this square is supposed to be over the whole thing, and I corrected this last year. So apparently I have a bum slide that just keeps coming back. But anyway, so imagine that this is the hypotenuse squared. Okay. Okay. So so if you multiply this out, there's an f squared on both. You get an f squared on both sides, so that goes away, and you're left with the radius subscript n. So any one of these radii is this part, n lambda over f, plus this term. This term is relatively small, so when what follows, I'm just going to use the first part, and we're going to leave this out. When we actually make them in the laboratory for use, we include this term. It's small, but we include it. But for the mathematics and how to understand the zone plate, it's not necessary. Reasonable accuracy to take this part and rewrite these formulas here. This was the original Pythagorean formula. This is with this thing expanded and getting rid of the two f squareds. And then with this term assumed to be small, taking the square root. And we're going to use this formula again in a moment, either as r squared equals n lambda f, or in the square root form, but we're going to use this in a moment. But this is telling us what we wanted to know. This is how the various radii are going to vary with zone number and wavelength. And again, in order to get the constructive interference, we want only the zones which add constructive interference. So alternate zones have to be blocked out. That's what's happening. That's why there's an opaqueness here. The ones that are a half wavelength, f plus a half wavelength, they would be adding destructively. We don't want them. So you're choosing zones that are going to add constructively. And by the way, just sort of incidental things, the area of every one of these zones is the same. So they're getting bigger in diameter, but they're getting thinner. So they're all contributing the same amount of radiation to the focal spot. Okay. Here's what one looks like. This is from Ansek Dinawat and Che Chang in their new lab at SLAC. Okay. And this is a zone zone plate made for hard X-rays. This is some of the formulas and some typical values for different things. So here's our zone plate formula. What we'll see in the next slide, but we won't actually go through the algebra, although it's all right there, is that the diameter of the zone plate is equal to 4 times the number of zones times the outer zone width. The focal length depends on the number of zones, the outer zone width, and the wavelength. The numerical aperture, the sine of this angle, depends on lambda over 2 delta r. So resolution is certainly going to involve that, etc. And then there's resolution, depth of field. The spectral bandwidth of the radiation incident can only be 1 over n. So if you have 100 zones, you want a spectral width, relative spectral width of the incoming radiation to be narrower than 1 over n, 1 over 100. If it's wider than that, the focal spots is going to spread out. And the reason for that is that the focal length of this lens, this is one of the big but the zone plate has 2 big disadvantages. One, its efficiency is of order 10%, a little bit less or a little more depending on certain factors. The other big thing is the focal length depends on 1 over the wavelength. So you better keep your spectral width kind of narrow so that the focal length doesn't get spread out too much, okay? Because then you'll have a blurred focal spot. It won't be as small as you want, and it'll be deeper. So, right. So that's why the bandwidth of the source should be kept to less than 1 over n. It just follows from these formulas. This is a good time for a question or a comment.
I have a question. In the picture you showed, and in some of the other pictures of those I've seen, there's a like a break, yeah, along the.
Yep.
What is that? What is the break for?
You know, I don't know what this particular break is for, but I could make some guesses. The various zones have to stand up. First of all, so they have to stand up, and so there's usually some structure underneath that's keeping them. And you may see it in other ways. In the top of the structure, there'll be some structure. So I don't know why this one is here, but you always see some sort of pattern, not a pattern that's as dense as this, but a pattern that's there for strength, to keep these things from collapsing, okay, in the manufacturing process. I think there's going to be another slide coming up, and it may show some of these features better. Okay, the only reason for this slide is that it summarizes a few of those relationships, but basically it just derives, if you had this formula, what happens when n goes to capital N, we're going to define the outer zone width. R sub n minus R sub n minus 1. So that's just the outer zone width. It's a definition. And then using that, we go through some algebra and show that the diameter, the total diameter of the zone plate is 4 times the number of zones times delta R. And the focal length has this formula. So that just comes from analyzing this equation. In fact, it's sort of interesting, I should have said it here. Here's a diameter. This is a zone plate with only 15 nanometers outer zone width. So that was state of the art a few years ago. Now it would be more like 10 nanometers, maybe even a little bit less than that. But the diameter is only 30 microns. You know, a human hair is between, let's say, 60 microns and 100 or 100 and something microns. 60 microns for a fine red hair, 100 microns for a black hair, for instance. So this is smaller than a human hair, so not big. Anything else I should have said? Yeah, the focal length is less than a millimeter. So, and the resolutions, typically the resolutions are about equal to the outer zone width. Usually a little bit more, but how much more? It depends on the illumination, actually, which I'll show you in a moment. But anyway, resolution to first order depends on outer zone width. Oh yeah, and there's a really important note at the top here. When you're designing a zone plate, where do you start? If you're going to make a microscope, what do you decide first? It's got all these different parameters in here. So what the top is saying, the most important thing is what material are you going to look at? So if you're interested in magnetic materials like cobalt or iron or something like that, the iron L edge at 700 and something, 780 V would be what you're most interested in. You want to work around that edge for absorption features. And so the first thing you do is you choose some photon energy that matters to your sample and your thesis. And with that comes a wavelength, lambda. The resolution is going to depend on the outer zone width to some degree. So, so you want to choose that. And then the bandwidth of the number of zones you can afford to have. You might want to have 1,000 zones so you capture more radiation, but the bandwidth of your source limits you to a certain number of zones. So if you're at an undulator, which has a natural bandwidth of 1 part in 80, then you can only have 80 zones. So that's how you set the wavelength, the outer zone width. It's going to set spatial resolution, and the total number of zones, and therefore the diameter and everything else. Okay. So besides focusing radiation like this and applying the Pythagorean formula on this side, you can also use a zone plate for point-to-point focusing and apply the Pythagorean formula to both sides. So here's Q's and here's P's, and just go through the algebra, and you get this formula that you've known from high school, that 1 over the image distance plus 1 over the object distance equals 1 over the focal length. And then the magnification is P over Q. So you could use this for demagnifying or magnifying. And the focal spot, this is where you'd have to do a diffraction calculation, which would be beyond our class. But if you apply the Kirchhoff integral and you do the diffraction calculations, which are in the chapter actually, you'll find that there's a J1U over U modulus squared gives you the intensity pattern in here, and this has its zeros. And so in the focal plane, you get what's called an Airy pattern, which is a bright central ring which has almost 90% of the power or energy, as I recall, and then a dark interference ring, and then the next bright ring, dark ring, bright ring. Now this is logarithmic, so actually it looks like this on a linear scale. Most of the energy is in this central radiation lobe, we call it, and this pattern is called the Airy pattern. And when one sees it, one recognizes you've got coherent radiation when you're looking at that. If you had a larger source size, this would all be washed out. Okay, and this is just saying that for a zone plate, based on this null, okay, this is the numerical aperture of a zone plate, period. Okay, the resolution we're going to find out for collimated radiation, such as shown here, or coherent radiation, the resolution is for this lens is going to wind up being something like 1.22 times the outer zone width. So if our outer zone width was 15 microns, this would say that you're sort of about 18 nanometer resolution is as best as you can do. And again, that's for collimated radiation. I'll show you a trick shortly that gets you to better spatial resolution, not using coherent illumination. So this is a case where you could have too much coherence. You could have a little less coherence would get you a little bit better imaging results. And this is just on depth of focus, depth of field. Here we're showing that the focal position is shown in the center, and this is an isometric view of what the focal distribution would look like just in the focal plane. But if you go off to either side, it's not quite so sharp and it goes down. And we define a depth of focus or a depth of field for imaging as when the area here, notice that the area is not zero. These are ray diagrams, which just cross at a point. But in fact, we're having a finite wavelength, so there's a certain blur to that. That's what's giving us this airy pattern right here. If you were to go to a different plane where the area of the focus was twice as big, so the area got twice as big on either side, that's called the depth of field here. This would be the depth of field. And where do I have it? Here is I've written the depth of field at the top here. This is for any lens that's of high quality and where the focal spot is controlled just by the wavelength and the aperture. The depth of field I'm showing as plus or minus a half lambda over the numerical aperture squared. So why do I go through the bother of putting this plus or minus a half? Why don't I just put a 1? A 1 would be the whole thing. It's because I forget. I'm forever forgetting, did I put in both sides or just one-sided? So I finally decided years ago, I would call it plus or minus a half. So this is 1/2, and this is the other half of the depth of field or the depth of focus, okay? Okay. And for a zone plate with having a certain numerical aperture, this is what the formula would be. So I told you also that the grating could have different orders and the zone plate can have different orders. And so here's radiation coming into the zone plate, and this is the first order focus, but this is m equals +1, but there's also m equals +3 and m equals +5. And after coming to a focus with much higher numerical aperture, which might be interesting, it then diverges and it would come to your detector or get into your image. So you need to block these other orders, and there's what's called an order sorting aperture right here. It's big enough that the main focus, first order focus, m equals 1, gets through with no problem, but the others are largely blocked. It's true that a little bit of their radiation can get through the hole, but just by area, it's insignificant, okay? And the different focal lengths are the focal length for m equals 1 divided by m. So the third order focus is only 1/3 the distance. This distance from here to here is 1/3 the distance from here, to F1, okay? And this would be a 1/5. So there are these various orders. If you don't want them, you have to deal with them. And if you'd like to use them, their efficiency, remember, is down. So this is maybe 10% for opaque structures. This would be 1%. This would be 1/25. Okay. So the reason we were blocking zones before with the opaque structures was because we didn't want the radiation that was adding a half wavelength, which would have been destructive interference, to get to our focal spot. So we had to block that destructive interference. But a different trick that could be played, and to some degree is often played, is rather than have opaque structures which are absorbing the radiation, have structures which because of delta and the refractive index and low absorption, propagate through with a pi phase shift. And if all of the zones which were previously opaque, now had a pi phase shift, we'd have twice as many contributions and in an electric field, and so we'd get 4 times the efficiency. So making phase structures has a great advantage. You could take your zone plates, if you could manage to have no absorption, you could go from 10% to 40%. That would be a really big improvement. That would be like increasing the current in your ring, storage ring, or the length of your undulator substantially. Anyway, this is what's required. This we calculated in chapter 3 what a phase shift would be for some photon energy or wavelength, and for some material and some thickness. This would be the phase shift. So to get a pi phase shift in each of these things, and therefore have all radiation adding up in phase, this is the thickness that you get. So it turns out that we can't make beta go away. But for instance, it's quite common in the soft X-ray region to use nickel zone plates, which are still partially absorbing, but they also have a partial phase shift. And you can increase the efficiency from maybe 10% to, I don't remember what the number was, but something like 20% or something like that. These would be future steps. Presently, what we do is what we call a binary zone plate, absorptive zones, okay? Well, maybe you could have less absorption by breaking this up into steps, okay, which sort of bend the wavefront a bit, okay? So that would improve the zone plate efficiency, or perhaps you could make a continuous shape, okay? And so these offer you various improvements, especially if there were phase zone plates with these different profiles. And this is showing that the 4-step, it says a 4-step phase zone plate could go to 80%, okay? So these are things for the future. People have made multi-steps like this, 2 steps and 3 steps, and they have seen improvements, but they're a bear to make. They're often made by just overlaying one zone plate over another. Others more sophisticated steps, but in general, we don't use it. It's, in the end, it's a lot of effort for minimal payoff. But in the future, that could change. And this is a set of zone plates. These are due to Anne Saktynowat, her PhD thesis at Berkeley. This is an ordinary zone plate. And then these is different zone plates which add to this formula. Same formula in all of these for the basic zone plate patterns, but something has been added here for functionality. And so Anne started on this because she went to a talk about biomicroscopy, and they were talking about the depth of field was too small for the CT scans. Okay, the depth of focus was less than the sample thickness. And so she came up with this idea. It's a really weird zone plate that had the property that it would what is the word? Degrade the focal properties. It was a cubic zone plate rather than a square. And the cubic zone plate would spoil the focus and spread the depth, and therefore spread the depth of field, and which goes as the square, so it was a big effect. And then because she knew what the aberration was that she put in, she'd correct for it in each plane and get back in the larger field, the longer depth of field, to get back the resolution. And these are other things. These add angular momentum. So if you're looking at magnetic materials, these so-called spiral zone plates add varying degrees of orbital angular momentum and are very good for looking at spiral structures or structures with spin, which are important for the transitions, quantum transitions. This is differential interference contrast microscopy, DIC microscopy. I think this one is called Zernike microscopy. And these are just some pictures, examples of those things. And to answer the question from before, I don't see any of the structures I'm looking for, the structural features that are used to support these. Okay, hard X-rays are harder. Soft X-rays are where zone plates are typically used, sometimes with hard X-rays, but not in general. Higher photon energies require higher Z materials, not a big deal, especially since absorption is less important at hard X-rays. But at shorter wavelengths, you could think you're going to get better resolution, but maybe not. But the thicker zone plates require higher aspect structures. They're not having as much absorption, and the phase effect is there. It's good, but it requires a thick structure. So in general, for hard X-rays, you needed to go from what the soft X-rays or EUV were zone plates which had thickness width to aspect ratios of aspect ratios typically 3:1 for soft X-rays, but for hard X-rays, it becomes much harder. You got to get to like 20:1 and 30:1 to get good efficiency. So that's a contrast for hard X-rays. And here's some structures that were made, same group, where these are 66:1 aspect ratios made for hard X-rays in the 30 to 50 kilovolt region. So that's a relatively new area. And these zone plates are made with an E-beam, an electron beam, a very finely focused electron beam. The focal spot should be smaller than the outer zone width, delta R. We typically say by a factor of 3. So if we had a 15 nanometer outer zone that we wanted to make, we'd want to have a 5 nanometer electron beam, which then writes a pattern in some molecular resist, breaks bonds, which later get flushed out chemically and then plated into those troughs to make some metal zone plate, for instance, like a gold zone plate or a nickel zone plate. And to get from one zone to the other, there's a blanker up here someplace, blanking plates that cut off the electron beam while you reposition it for the next zone. You write one zone after the other. Now we have a little bit of time left, and there's a few more things to say, which has to do with diffraction, diffraction and resolution. But let me go to the other slides, which are more interesting. Resolution, you've probably heard this in some other classes or reading some books, but if you have a lens which is imaging one or two sources, here it's shown two separate point sources, which are being collected by a lens with a numerical aperture shown here by the angle theta and imaged back into a plane on a CCD detector. And if you image them one at a time, you'd get an Airy pattern like this. And these things we're going to say are point sources, so they're each coherent, but they're mutually incoherent. Somehow or other, their phases are randomized, okay? So when you image them back here on the CCD, they appear as separate Airy patterns. And resolution, spatial resolution, the most common measure we have that we say things are resolved is the so-called Rayleigh resolution. And in the Rayleigh resolution, you bring the two close enough together that their Airy patterns start overlapping. And when they're overlapping just so that the peak of this one, the brightest part of this one overlaps with the first dark ring of the other, it will look like this. So this would be the total intensity pattern. Remember, they're mutually incoherent, so we're adding intensity. So here's one Airy pattern coming down here, and here's the other Airy pattern. And when you bring them close enough together, adding the intensities, this dip is called the Rayleigh dip. And it's when, again, when you match the peak of one with the null of the next, okay? It gives you a 26% dip. And that resolution, if you put in the angles and everything else, is 0.61 lambda over NA. So this is for any optical system, okay? And so again, if you have a bigger angle, larger collection, not so much collection angle, larger numerical aperture by making the lens diameter bigger for the same focal length, that the NA would get larger, the resolution would get smaller. You can see smaller features. So in general, that's the way we define resolution, is by the Rayleigh test, right? It's not, there are other ways of defining it, but it's absolutely the most common. So here's another example of that. Here's our two point sources of light that have been imaged, and they're separated by some distance. They each have an Airy pattern. And when you bring them just together, this is the Rayleigh criteria, okay, where you can see that the maximum of one is matched with the null of the other, okay? So let's see. Here's a null. This one this one over here. This one's null is right here, and the dashed line is showing it's matched. So that's the Rayleigh criteria. And this is what happens if you had a periodic bunch of these things? Well, we often use gratings or even zone plates as test patterns. And so we're interested in not just 2 point sources because we can't make point sources, where we often use periodic patterns like gratings to measure. And in that case, it's basically like you have a whole bunch of these features coming together. And the point of it is that the equivalent of Rayleigh is actually a period, not a half period. So this is a little cheat. All the zone plate people all claim their resolution as being just a half period, one opening of the zone plate, something like delta R. But in fact, we should be looking at a period, okay? This is an old paper. It was a PhD thesis by Wei-Lun Chao some years ago, but he very nicely got a Nature article out of it where this was, the outer zone width was 15 nanometers, and these are 15 nanometer lines and spaces. So a period would be 30. So that's not cheating. And I'll show you in a moment, though, how you actually get a little bit better than what I was telling you about in resolution. So this was a nice publication for his PhD thesis. And this is work from Bessie in Berlin, which now has one of the best microscopes in the world. They and Alba in Spain, but the team in Bessie is really the world's best. And this is showing a result they did with a 20 nanometer zone plate, but they imaged in third order, and they were able to see features down to 8 nanometers, okay, a period. Okay. So that was quite good. But here's one of the things I wanted to make sure that we got done. This is our normal diagram, which I've just been showing, or something like it. There's light coming in. There's some object here, some squiggly biological thing, or a grating, or a multi-layer in transmission, something like that. There's light coming in. It diffracts off the period D. So this is our grating equation for this angle theta. This is in transmission. And then this is imaged down here. And that would give us the resolution we talked about before. But in fact, if you came in with your radiation at an angle theta, okay, you could actually look at things which were half as big, smaller. So by controlling your angle of illumination, you could actually diffract off this thing. So this would be your straight through radiation, and diffract through an angle 2 theta rather than theta, and you could see objects that are smaller. So illumination can buy you up to a factor of 2. Actually, you lose, it doesn't go all the way to a factor of 2 because your radiation is just about hitting the edge of your lens, but you can do pretty good. And here are some diagrams. So in fact, what we do with a microscope, which is done in lithography or high quality microscopes for biology labs or something, you use various kinds of illumination. You really play illumination to the max. So besides getting a good lens and everything else, you optimize your illumination. And for lithography, this is, and computer chips, this is a major issue. And of course for biology also. And what we do is we talk about this angle theta, we'll call this the numerical aperture of the lens, okay? The numerical aperture of the objective lens of the microscope, okay? But there's an illumination half angle also. This is often called, there's often a condenser lens here. And so that would be the angle on this side is called the numerical aperture of the condenser. And there's a non-dimensional parameter, sigma, which is the ratio of these two things. So for coherent illumination, this would just be parallel light, and this would be 0. And so sigma equals 0 would be coherent illumination. And you can have whatever angular control you want here, but being motivated by this performance, you try one of these others. And so 2 things. This was a calculation done by O'Toole who was a PhD student with Andy Neureuter in Corey Hall. And this is showing a knife edge that's been illuminated. And if it's overly coherent, you get what we would call in mathematics, Gibbs phenomena. You have this overshoot. So this dark line is coherent illumination, It's not actually sigma equals 0, it's sigma equals 0.2 is the solid line. And it's not the best resolution, it turns out. Okay, it turns out, and these, we don't want infinity either, but if you look at some of these in here in the middle, they have the same slope here, so that's very good, and they don't overshoot and give a misleading part of the image. They more or less follow it better. So in this case, in many of these cases, an optimum is to get something in this region. Now, we are running out of time, and I don't know if I want to show this one or not. Let me just look. Yeah. This is just showing a little bit more detail about point source, illuminating point sources, which we've just looked at before. A single point source, 2 at the just Rayleigh resolve, a whole bunch of them, so it looks like a periodic structure, or rather than have a bunch of point sources, have a diffraction grating, and what does it look like? And how well an optical system, this could be many optics here, how well it can re-image this object onto over here into some other plane at larger magnification, so they're bigger. Whether it can do this with full amplitude or whether it starts to get graded is sort of a parallel to what's going on over here. It's not 100% modulation, but it still has all the steps and it's close. And then when these things get too close together, you have less modulation, okay? And so out of these things, we make diagrams which show how the modulation falls off with periodicity as you approach resolution limits. This is the refractive lens I told you about, the compound refractive lens from the Sneaker-Fs. And this is what some of those patterns look like. So for instance, they use them a lot at hard X-ray synchrotrons. They run them maybe 10 keV photons out of an undulator, and they'll use a whole row of these to focus the radiation. And each one of these things would have a slightly different structure here. So there would, you could vary the focal length just a little bit to get just the right focus on your sample. So they use them for alignment of optical systems a lot. And this is a crystal. We're down to a minute or two. This is a sodium chloride crystal, is meant to be pictured here with various planes that you could diffract off. But what I wanted to say here was that here are some calculations from Boris Batterman and Don Bilderback at Cornell showing reflectivity for different photon energies, okay, from a silicon 111 crystal with incident X-ray energies of 5, 10, 20, and 40 kilovolt. And you see, here's 100% reflectivity. So you see, and there's quite a few cases here where here, even the green one at 7. Oh, that's in microradians. The green one would be, I guess, 20 kilovolts. You're up above 90% reflectivity. So even here, the red one at 10 kilovolt, a very, very common wavelength. This is giving the angular width of the crystal. If your source is broader than that, for instance, it just won't reflect outside of those angles. But within that, within the 10 microradians of this radiation, again, what is the red? It's not 10. Oh yeah, 10 keV. It's getting up to, these are 2, so you're around 97% reflectivity. So they do marvelously well. So this is one of the reasons that the hard X-ray synchrotron beamlines are far more efficient, factor of 10, than the soft X-ray ones. And that, by the way, remind you that the reason the crystals diffract so well is that you're diffracting from the valence electrons. This is from argon, as I recall. So this is a radius versus electron radial charge density. The reason the crystals work so well is because you're scattering from the outer electrons, which don't absorb. Their absorption energy, they're essentially free electrons as far as a 10 kilovolt X-ray is concerned. Whereas the core electrons, which would absorb, are so tightly constrained by, you know, a radius of A over Z, the Bohr radius over Z. The core electrons don't actually see the radiation because of this interference effect. The incoming radiation and the outgoing radiation interfere. They form a standing wave, which is shown here, where the highest electric fields are in the middle of the planes, and the electric fields at the planes where the core electrons are confined, very small. So that is an important part of why you get such high efficiency. And that's all I was going to say for today.
Sir, how do you know if the source is too large that the reflectivity, it won't get any reflectivity?
I couldn't hear you. It was a little bit muffled.
Yeah, how do you know if your source is too large that you won't get any reflectivity?
So yeah, so this is saying that this crystal, for instance, the green one, has an acceptance of 7.8 microradians. So where is this crystal compared to your source? And this is very much involved, not quite involved in the coherence, but the same issues. What is d dot theta, lambda over, you know, something or other. And when you look at that, so you have your crystal is some distance, maybe 20 meters from the undulator source. How big was the source at that point? And that gives you an angle, and compare that angle to the acceptance angle of the crystal. And so you'd find out that probably, so for instance, at argon, all the synchrotrons are going to do a major upgrade. Argon is a hard X-ray facility, and they're going to go to close to a much smaller ellipse, eccentricity ellipse than before, and they're going to make this source smaller, so they're going to get a lot more radiation into the smaller angles than they did before, because they're making their source, the ALS, it's 100 times smaller. I think it's like 30 times smaller at argon in the vertical direction, in the horizontal direction. So depending on your crystal orientation. So that's what you're doing. How does this angle of acceptance compare with the distance and size to your source?
Great, thank you.
By the way, I told you that the HKN people were going to come about the course evaluations. They're just going to come for the last 15 minutes on Thursday. So we have most of the class to do some imaging discussion, and I'll post the slides for that before class. Okay? Any parting thoughts? Okay, see you on Thursday.